guys, this is our hurricane makeup lecture for day 2 on section 7.2 trigonometric integrals. Some comments before I really get going here. One, you will notice that again we're still skipping around. I'm still trying to make sure that we get the easier lectures out of the way by video so we can work on the harder ones together in person. You don't need pretty much most of the prior sections to this, except for we will need to know how to use sub. With us skipping around here, you will also note section header says 7.2a on this slide. This is going to be a 2-day lecture. We are going to spend a second day looking at this and working on kind of similar problems. Disclaimer, kind of like last time, if you're a person that likes reading a lot better than you like videos, there are online notes posted, so PDFs on the Moodle page. Check the lecture notes section on Moodle. Test 1 folder, your trigonometric integrals notes should be in there. Final comment that I'll note, just so nobody freaks out, no quizzes today. I'll go easy for this particular time and not saddle you guys with a lot of extra stuff to come back to. Okay? So, all that junk out of the way. Section 7.2, what are we doing here? Well, here's a little bit of a unit shift going on. The previous section focused mostly on applications of integrals, so the entire chapter did really. We were finding areas and volumes and average value. Chapter 7, on the other hand, is focusing largely on integration techniques. So, if you have just an integral that you want to compute, and maybe it's a tricky one, how do we deal with it? We're going to learn some techniques today that involve applying trig identities alongside U substitution. So, I'll go ahead and recap how we do U substitution. You guys have probably seen a problem like this before. I have this sine squared of x cosine of x integral that I want to take. You notice that I've got a composition of functions floating around here. So how do we deal with those? Usually U substitution. We've always said if you're trying to do a U sub, we like picking inside functions for my U. In this particular case, if my pen was working better, this would be the sine x function. The derivative of this guy is going to lead you to your du, so I'll take the cosine function, and since it's a du, slap a dx on the end. This will give me something that I can directly substitute into my integral, so here I no longer have sine squared. I really want to think about this as u squared. I no longer have cosine of x dx on the end. I want to replace that with the du that I said it was equal to. And at this point, you should be able to actually antiderive. And then once you antiderive, we should be able to replace my u's with, whatever appropriate substitution I made. So my final answer in this case will be sine cubed of x over 3 plus c. Now, where do these identities come in? Sometimes your compositions end up being kind of a pain in the butt, okay? Case in point, this next example, I'm integrating sine cubed of x. I do still have a composition floating around here, but you'll notice that if I tried to make u like I did in the last problem, we get an issue because there's not really any leftovers here for me to substitute my du into. So I'll point this out that this is a potential issue here. If I tried something like u is sine x, try the obvious, u is the inside function. This does not work here because there's no room in this problem for a du to fit, right? So here's the goal of this section. We are creatively trying to make room for du's, or point out where my du's should be so that I can appropriately use u substitution. Now, for this particular question, I will offer a set of steps that we should try, namely 3 things, and I'll kind of list them out here. What I'm going to try to do is I am going to save one of these sine terms for my du. If I do that, I have a couple other sine terms floating around. What I'm going to do with those is rewrite them. Okay, rewrite the rest of your integral with a trig identity, namely the useful one here is going to be sine squared theta plus cosine squared theta is, what is it? This is usually a familiar one. It equals 1, okay? This guy equals 1. And then once I rewrite the rest of my integral, then and only then try u sub. Okay? So, without further ado, I'll go ahead and get started. If it was not clear by what I meant with saving a sine x term for my du, this is what I mean. I've got 3 copies of sine because I'm cubing it. I'm just going to split these into 2 pieces. I've got sine squared times sine dx. Now, usually it is not conventional for us to simplify in this direction. Usually we would multiply sine squared by sine and simplify it to a cube, but we're not trying to clean it up in that manner. We're trying to give ourselves a way to u sub. So I'm going to go backwards from how we usually would to try and set up a u substitution here. So we have done this first step. Next thing that I want to do is rewrite the rest of my integral using that trig identity. Now, you'll notice that I've got a sine squared here, and I've got a sine squared in this identity. If you solve for sine squared in that identity, it'll give you something that you can replace that initial first part with. I can think of this as 1 minus cosine squared of x, okay, times sine of x dx. And you'll notice that once we performed this rewrite step, now we've actually set ourselves up pretty well for a u substitution, right? I've got a composition involving the cosine function where cosine is now my inside function. This will set me up for a u sub where du is negative sine of x dx. I will have to correct the coefficient on that. And if I scroll down to give myself just a little bit more room, once I substitute everything in here, this is no longer going to be 1 minus cosine squared, it's 1 minus u squared. And this is no longer a sine x dx on the end, this is minus du. And if I wanted to clean this up to antiderive, I could. I can think of this as u squared minus 1 that I'm antideriving. This should give me u cubed over 3 minus u plus c, or if I recall that u is cosine, this is cosine cubed of x over 3 minus cosine of x plus c. Okay, so we got our answer, okay, because we did the appropriate u substitution here. How did I know to do any of this? Right? Those 3 steps that I suggested above, they kind of came a little bit out of nowhere, although I did try to justify why we did them as we worked through the problem. You know, when do I know that I need to do this? You know, are there other sets of steps that work different for different problems? You know, what explicitly do I, you know, attempt for different trig integrals? Is it always going to be the same? No, in this section, there are 4 primary tricks for dealing with certain types of trig integrals. Today's lecture, I'm going to cover 2 of them. We'll get to the other 2 next class. The trick that we focused on for this particular problem, I'm going to go ahead and call trig integral trick number 1. I'm going to give you a red flag that points out, hey, this is the trick I need to use, and then I'll give you instructions for how it works. Okay, so here, my red flag for this particular trick is up top. If my integral has a bunch of sines and cosines, particularly if they're in a product together, if it has a bunch of sines and cosines, at least one of them is to an odd power, what I'm going to do is, you know, the set of 3 instructions I gave you. We want to save an odd-powered term for a du. I want to rewrite the rest of the integral into the opposing trig term using that trig identity, the Pythagorean trig identity. And then I want to close this out with a u sub. Okay? We can actually go back to my previous example really fast and just outline where each of these steps happened and, when I noticed that I needed to do this trick. So if I click back here really fast, first observation is that this guy is a trig term to an odd power. Okay, it's sign cubed. So that cube is going to be our red flag that we needed to try these 3 steps that I named. Okay, first step was save one of the odd-powered trig terms for your du. Well, we only had the sine function appearing, no cosines. So that meant we had to save a sine for my du. This is why I pulled this guy off to the end here. That was step number 1. The next thing that I wanted to do was rewrite the rest of the integral, which this is your rest of your integral. Rewrite the rest of the integral using your trig identity. This is what we did on step 2. And then the final step is this should, ideally, if you did it right, set you up for a nice u substitution with either u equals a cosine term or u equals a sine term, okay? You should just have the one trig term that you saved off by its lonesome, and everything else should be written in terms of the other trig term. That's why this is really nice for u sub, okay? Let's see if we can start this from scratch on a different problem so we can work through each of these steps together. Sine squared of 2x times cosine to the 5th of 2x. There's our odd power right there. So, if I'm doing my steps in order, first thing that we should do is save an odd-powered trig term for a du. Okay? What that means is whichever of the trig terms has an odd power, you want to leave one of those guys on the end with your dx because you're hoping it's part of your du. But, obviously that's not the only cosine term we have. We do have to split this apart so it's grouped appropriately, right? So if there are 5 of these cosines in the beginning and I save one on the end, that means that there's 4 of these left over that I need to worry about rewriting. Next thing that I do after this step is I'm hoping to rewrite my rest of my integral in the opposing trig term. So here, that means rewriting everything in terms of sine. Now I want to rewrite this in the opposing trig term using that identity, sine squared plus cosine squared equals 1. So in this particular case, I will give you a hint. How the heck do I do this when I need to rewrite this cosine in terms of sines, but it's to a 4th power? Here's a trick for helping you guys with general even powers. I'll offer this up here. If you have a general even power, let's say a to the 2n, you can rewrite this so that it involves a square if you're a little bit sneaky about what you do with your exponents. Okay, so I'm going to do that trick right before I do the identity, right? If my goal is to rewrite everything in terms of sine, that means this piece gets left alone. My cosine to the 4th, I just said we were going to try to write it as a square, but we would have to do it in a sneaky way. Here, I don't really have to do anything with this cosine 2x dx on the end. We said that we were saving that for a du, so I'm not going to touch it. So notice that happening was really me making this trick happen right here. The next thing that I want to do is apply this identity, right? So I want to apply my identity to this expression that is in the middle here. And if I do that, well, it's not affecting my sine squared term. We said we wanted to rewrite everything in terms of sine. Cosine squared we can note is the same thing as 1 minus sine squared. And this cosine term on the end, again, we said we were saving it for du, so we're not going to do anything with it. At this point, you should be able to notice that that was where we applied this identity, okay? But more importantly, we're actually set up to do our u sub pretty perfectly now. We have all these compositions involving the sine function. Okay, so I'm going to go ahead and use u equals sine. And then the rest of this is just going to be setting it up like a regular u sub problem. Okay, be careful with your coefficients so you make sure that you're not messing up your constants. This is going to be a problem that I have to coefficient correct for, so I will make that observation. If I go to substitute everything in here, I no longer have a sine squared of 2x term, I have a u squared term. I no longer have a 1 minus sine squared here, it's a 1 minus u squared. Don't forget that's being squared. And then the cosine 2x dx on the end is something that's turning into a half du. Now, this is a doable integral. We just need to make sure that we clean it up appropriately. All right, so be very careful with, say, moving your terms around, foiling. Okay, so what's happening here is me actually multiplying that square out. And on this next step, I'm going to go ahead and distribute everything through. We'll get a half u squared minus u to the 4th plus a half u to the 6th. Watch your powers. Finally, from here I get to actually antiderive, so u to the, oops, wrong digit here, u to the 3rd over, if I divide by 3, that'll be 6. U to the 5th over 5, and here u to the 7th over, if I divide by 7, 14. And then my final step is, of course, going to be to plug in my u, which we said was sine of 2x. Right, so sine cubed of 2x, sine to the 5th of 2x over here, and a sine to the 7th of 2x over here. Okay? Now, final comment on this odd trig term setup, so integral trick number 1. Sometimes you get a choice in how you set these up. Okay, I mentioned that the red flag for trick number 1 is that you have to have an odd power. You might have one odd power like in the previous examples, or there might be 2. And if there are 2 of them, you have a choice. Either you get to save a cosine and hope that your rest of your problem can turn into a u is sine problem, or vice versa. And that's okay. You might get different looking answers at the end, but they should actually be functionally equivalent. Okay, and I'll demonstrate with this particular example. Now, this is not an example that I actually have to do identities on, but it does count as a odd-powered trig problem. Both of these are to the 1. That means I could save either of these for du, and that also implies that I could actually use either sine or cosine for u. So I'm going to try this one of 2 different ways, and we'll see what we get, right? If I try this with, let's say, u is sine, this is actually probably the easier way to set up the problem, just because when you find your u and your du, there's no coefficient correcting. This is pretty direct. You know, about as simple of a u sub problem as I could potentially throw at you guys. So this is going to give me a sine squared of x over 2 plus c. Now, if I want to, this is not the only way that you could set up a u for this problem. You could also go the other way around. Granted, this direction is a little bit trickier because you get a negative derivative. That means that you will have to constant correct. So I'll get minus du is sine x dx. So that when I substitute everything in, I now have a negative sign to contend with, which is slightly different from the previous case. Also, I'm dealing with a different u, so when I go to substitute stuff back in, very obviously my antiderivative looks different. What the heck? I got two different answers. Well, they look different. The reason I wanted to point this out is to also emphasize to you guys why I keep saying that C is important to remember. Sometimes it can actually contain a sizable bit of information. I'm going to scroll down just a little bit here to make some comments about this. Namely, this identity that we've been using, you know, that sine squared plus cosine squared equals 1. Well, if I throw that identity at this particular problem, I'm really getting 1 minus cosine squared up top here. And another way that I could interpret this is minus cosine squared of x over 2 plus a half plus c1. Notice that the functions that we're dealing with now look a lot closer to each other. It's just that the only thing that's different is the c that's on the end. So notice if we changed up the c, or if we used a different c, or if we didn't include c at all, we would have had different answers. Okay, so those different answers with the c, without the c, with a different labeled c, they're meaningful. Okay, so this is one of the reasons why I keep getting on you guys. Don't forget the plus c on the end. It actually means something. It'll allow us to make up for discrepancies like this if you pick different options of u. Okay, so both of these are correct. Both of them are true. You don't have to do both of them, but I did want you to recognize that in cases where you have an option, maybe your answer may come out looking a little bit funny from how you were expecting it to. Okay? Other cases. What if there are no odd powers, right? We saw a couple examples where there was one odd power. We just did an example where there were two odd powers. What if there are none? Trig integral trick number 1 called for odd powers. So what if that doesn't happen? Well, you can't use trig integral trick number 1 because here's the idea. I'll give you guys a pretty rudimentary example here. Let's just say I throw out a generic cosine squared function. The first step of trig integral trick number 1 was to save something for a du, and you'll notice that if we try that here, the leftovers of the problem that we need to rewrite will not let us apply Pythagorean identity, right? Won't allow, sine squared plus cosine squared equals 1, because I can't get this in that format without maybe doing some sort of trick like square root of cosine squared. And in that case, I'm actually making my problem harder because I'm introducing square roots, and we do not want to do this, right? So basically in cases like this, don't do trick 1. It's only going to, make your problem harder. What you want to do instead is what I'm going to call trig integral trick number 2. Red flag for this being no odd powers, so sines and cosines have to only be to even powers. Now this is going to work a little bit differently from your previous trick. We're not worried about saving stuff for du. We're not worried about rewriting just one of the trig terms. We're applying these new identities, the half angle cosine and half angle sine identity. We're applying these to everything in the integral. Okay, apply these to all of the terms in the integral indiscriminately. Now, once you do this, we get to simplify, and here's also where this trick is a little bit weird. We basically get to regroup at the end and figure out where to go from there. Sometimes you can directly integrate. Sometimes you have to do trick 2 again. Sometimes you have to do trick 1 again. Sometimes it's sort of an iterative cycle, but basically the idea here is use your half angle identities, simplify, and then you really want to try to integrate, okay? And what I mean by try to integrate is we're going to have to see, right? Sometimes we can integrate, sometimes we have to start over. So to highlight what I mean by this and how it looks, let's try an example, okay? Sine squared, 6x, no odd powers, okay, only an even power. So I've got my identities over here at the ready for us to use. If there were sines and cosines to even powers in here, say all of them of 6x, I would want to throw both of these identities at my problem, but there's only a sine term here, so I just get to rewrite the sine term, okay? So step 1 is basically that big old rewrite step. Rewrite with these identities. Now, I've got a sine squared. That means that I'm using this guy down here, okay, this sine squared identity. And I'm going to turn this into 1/2 times 1 minus cosine of 2 theta, but how that works is this. Whatever angle you start out with, that's getting doubled when you write this identity out. We started with a 6x. That's going to turn into a 12x when we write our identity out. At this point, I've got my identity written. I need to see about simplifying. The only thing I can really do here is distribute that half through. And at this point, I basically get to try to integrate. See if we can do it. If we can, great. If we can't, see if we need trick 1 or trick 2. Turns out this one does utilize basic rules. I can slap an x on the 1/2. I will hang on to my 1/2 coefficient. I will note that the antiderivative of cosine is the sine function, but this is a cosine of kx problem. So I do have to divide by my constant coefficient when I antiderive. Okay, so if you guys want a more finalized answer here, you probably should clean up your constant coefficients. Final answer is going to look a little bit something like this. Okay. Let's see if I can try this on just another couple examples to make sure that we got the pattern down. Cosine to the 4th of 3x. You'll notice I don't see squares here, but I do see only even powers. We can do the same sort of trick that we did before, right? So same kind of hint that I gave y'all. If you have a general even power and you want to rewrite it to use one of these square identities, manipulate your exponents, okay? So this, this integral, if I want to rewrite this out, step 1, I really want to apply my identity, but I can't do it directly yet, so it's going to take me a couple steps. I will start off thinking about this as cosine squared of 3x squared. And then when I do that, and I go to substitute my identity in, again, we're using the top identity that I wrote down for reference up there, 1/2 times 1 plus cosine of 2 theta, okay, except for we started out with a theta and we need to double it. If we start out with 3x, I probably want to double 3x. Let me get my 2 deleted here. If I double 3x, I'm going to get 6x here. I'll save myself writing that step out again. Okay? And I guess if I'm being really, really careful, that whole thing needed to be squared. Okay? So, cosine squared term, I have to square that entire thing. Now, step 2 was to actually simplify that, which is why I was trying to be careful in that last step about what I needed to actually multiply out. If I square both of the pieces here, if I square my 1/2, and if I square that, binomial looking term, if I FOIL that out, now I can also distribute this through. Okay, if I do this, I have a 1/4 plus a half cosine of 6x because of my 1/4 and 2. I also have a 1/4 cosine squared of 6x. I've simplified this about as much as I can. I can't combine anything else much further. So my last step is going to be to try to integrate, but I need to make an observation here. We've got another one of these even powered trig terms, right? What that's going to tell me is we need to do the identity again on that last term. So this is what I meant by, sometimes we can jump right into it, sometimes we have to kind of start over again. We're basically taking this identity and putting it in that last term one more time, okay? So this is an identity that y'all are going to have to eventually learn. So yeah, it's off screen right now, but this is something that we're going to need to know. So when I go to substitute this in, this is a 1/2 times, you said that cosine squared turned into 1/2 times 1 plus cosine 2 theta. Here that's going to be 12x. And if I want to clean that up, okay, kind of repeat the process again here. There's a lot of copying, okay, a lot of this really isn't changing, but I do get to distribute some stuff, namely this 1/4 and this 1/2 on the 1. That means I've got an 1/8 here, and I've also got this 1/4 and 1/2 on my cosine term, so I've got a 1/8 there as well. And if you want to simplify one more time before we jump into things, you may note you've got two constant terms here. If you wanted to regroup those, that would save you another term to antiderive in a moment. Okay, so, final step, I actually get to antiderive this. Most of these are dealing with basic rules. The constant term just gets an x slapped on the end. These cosine terms, if you really wanted to do u sub on them, you could, but I did give you a way to treat these as kx functions. I could interpret this as 1/12 because I need to divide by the k. 1/12 sine of 6x. And similarly, I can interpret this guy as 1/, have to divide by 12 here, so 96, 1/96 sine of 12x. And then this was indefinite, so I need a plus c. Okay. I'll try one more of these, okay, just to establish what I meant by, you have to apply the identity everywhere. Even powers only in this problem. I've got a sine squared and I've got a cosine squared. So when I shove both of these identities in here, here's what it looks like. I've got a 1/2, 1 minus cosine 2 theta, so 1 minus cosine 2 pi x. And then I've got a cosine squared that I need to do this to, so a 1/2, 1 plus cosine 2 theta, so 2 pi x. Notice that the primary difference between these identities that I've given you guys here is that, the cosine squared one has a plus sign, the sine squared one has a minus sign. So they both look really close. If I go to clean this up, I'm going to make an observation that should make it a little bit easier to simplify. My 1/2s combined will give me 1/4. I've really got a 1 minus cosine 2 pi x and a 1 plus cosine 2 pi x to multiply out. that's actually going to give me a difference of squares. So you could sit there and FOIL this out, or we could try to do this a slightly more efficient way. I can view this as a squared minus b squared, so 1 minus cosine squared of 2 pi x. If you want to give yourself fewer terms to deal with, like maybe I don't want a cosine and a constant term floating around, this is totally optional, but, you know, we could try the Pythagorean identity here. This will give us one less thing to worry about. 1 minus a cosine squared term is basically going to be the same exact thing as a sine squared term. And now that I've got the sine squared term, I'll make the observation that we basically need this trick 2 again, right? We have still got a square, trig term in our integral. So from scratch, you know, I'm basically going to have to apply this identity, right? Rewrite my sine squared as a half times 1 minus cosine of 2 theta. 2 theta here is 4 pi x. At this point, you know, after you substitute, we want to try to simplify. If you want to pull out that coefficient, if that would help you, that's totally fine. So there's a little bit less clutter happening here. But after you simplify, you get to see if you can antiderive, and here there's nothing stopping us from antideriving, okay? If you want to antiderive, your 1 turns into an x. Okay, over here, your antiderivative of cosine is a sine term, but this is a cosine kx problem. You do need to divide by k. Okay, but when I antiderive and get sine, I copy over my inside function. Okay, so this is going to be my antiderivative. It's indefinite. Just remember that you need to throw a plus c on the end. Okay? If anybody has questions on this stuff, do feel free to shoot me emails with questions and things. I will reiterate, if y'all are emailing me for help with problems, it helps so much for me to give you guys feedback if you actually show me what your work looks like. Okay, so if you're working on something, you get stuck, send me like a photograph or like a screen cap of whatever you've been doing, okay? That'll let me give you guys feedback on how to work through these problems. And also, if you're stuck on some of these techniques, we're going to be doing very similar tricks for some other stuff with the next lecture. So do feel free to, you know, see if some of it sinks in a little bit then as well. Till next time, guys.